All right. Hi, everyone, and welcome to Wednesday Night at the Lab. My name is Dylan Brewer, and I'm a student hourly worker here at the Biotech Center. On behalf of the Biotechnology Center, welcome. And UW-Madison Division of Extension, Wisconsin Public Television, Wisconsin Alumni Association, and UW Science Alliance, we all thank you for your attendance. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce you to Tim Schmidt and Gene Phillips. Tonight, they're going to be talking about Wisconsin's role in Earth imaging from stationary orbit. Before we get started, we're going to ask them a couple questions. Where were you guys born?
So I was born in St. Louis Park, Minnesota.
Awesome.
And I was born in Marinette, Wisconsin.
Okay. And where did you attend high school?
The fine Hopkins Dwight D. Eisenhower High School.
Wow.
St. Joseph's Academy in Green Bay.
All right.
Yeah.
And where did you guys attend undergrad?
So I went 2 years to St. John's University in Collegeville, Minnesota, and I transferred to the fine University of Wisconsin, Madison.
St. Norbert College
All
for
right.
me.
And what did you guys study while you were there?
So when I transferred here, it's a degrees in meteorology.
English and French.
Awesome. All right. And if you went on to get any advanced degrees, where did you get those?
So I also got my master's degree here. Then called the Meteorology Department, which is now Atmospheric and Oceanographic Sciences.
And I got my master's degree from UW-Madison and in information studies.
All right. Awesome. Thank you. Everyone, please join me in welcoming Gene Phillips and Tim Schmidt.
So thank you for that warm welcome. And it's really an honor to be back at Wednesday Night at the Lab. Tim and I have a whirlwind story for you this evening. And so without further ado, I think I'll get started. Good? Okay. Taking pictures of the Earth. So what does it take for an idea to take root, to become the first? And beyond that, to change the world? Like any story, the story of how UW-Madison professor Werner Suomi, the father of satellite meteorology, started taking pictures of the Earth is really multiple stories rolled into one. His work wasn't done in isolation and was influenced by people and events around him. Part of that story centers on UW-Madison, of course, because UW-Madison has always been a hotbed of innovation. The first weather forecasts on radio were broadcast from Science Hall in 1921 from the 9XM studio, the predecessor to Wisconsin Public Radio. Wisconsinites could now get weather forecasts over the air rather than in the mail. And it was especially advantageous to the state's farmers, of course. Today, we probably don't consider a time when we did not have them. Harry Steenbach developed a process to enhance vitamin D in food through UV radiation. The discovery was picked up by the Quaker Oats Company in 1927, and the process was used to fortify breakfast cereals. It was also the first license agreement of the Wisconsin Alumni Research Foundation. And Arthur Robinson developed a map projection that shows the entire world on a flat surface and reflects the true continent size. Until then, putting a sphere on a two-dimensional surface had been a challenge, and it made land masses like Greenland appear inordinately large. James Thompson at UW was the first to cultivate embryonic stem cells in a laboratory setting and forever change medical science by opening the door to regenerative biology. And also paving the way, of course, to changing the course of disease and its treatment. The list goes on, but the commonality among all of these firsts, and the first that we'll talk about tonight, is an exceptional person with an exceptional idea who emerges at a critical moment in time with an idea that changes the world and forever shifts our perspective and our expectations. So Werner Sumi, who is considered the father of satellite meteorology, was born and raised in Eveleth, Minnesota, in the northern mining area of the state. His family was not poor, but like many families, suffered financial hardships. And it was his brother, Anard, who dropped out of school to help support the family and send Werner to the Teachers College and then later to the Winona Teachers College. Sumi always said that he owed a debt of gratitude to his brother. About his performance at school, Sumi also said, "I don't recall that I was a superstar pupil, but I wasn't dumb either." He became a junior high and high school science teacher and taught in the towns of New York Mills, Sleepy Eye, and Faribault for about 4 years after he received his teaching certification. He made his way to the University of Chicago as a 9-month cadet in a 9-month cadet program via the civilian path. He wasn't particularly interested in studying meteorology, but when he realized that the study could also involve instruments and observations, this changed his mind. In 1948, Sumi was invited to join the faculty of the newly founded meteorology department at UW-Madison. He was also weighing an offer from Iowa State University, and considering which offer to accept, he asked a friend who was a native of Iowa, when people in Iowa go on vacation, where do they go? And Wisconsin was his friend's answer, and so the decision was made. So while he was at the University of Chicago, Sumi devised an experiment to measure the heat budget of a cornfield that would later serve as the basis for his dissertation. He is seen here, second from the right, viewing instruments to measure heat, moisture, and wind in the microclimate of a cornfield in Ames, Iowa in 1947.
July 1st marks the beginning of one of the great scientific adventures of our time, the International Geophysical Year. During this period, which will actually be 18 months long, the scientists of the United States will join their efforts with those of the scientists of some 60 other nations.
So in 1955, the National Academy of Sciences and the National Science Foundation announced plans for the construction of a small, unmanned, Earth-orbiting satellite vehicle to be used for basic scientific observations during the forthcoming International Geophysical Year. And with these words, a new era was launched. The year would in fact be an 18-month period from July 1957 until December 1958, during which scientists around the world would coordinate research efforts, and meteorology was one of the topics. In 1956, Harry Wexler, who led the US Weather Bureau, submitted an idea for an experiment to measure the Earth's radiation budget that would be led by Werner Sumi. Also during this time, the Soviet Union launched Sputnik 1 in 1957, igniting the race to space between the two nations, and NASA was formed in 1958. This environment proved to be fertile ground for the young field of satellite remote sensing and provided opportunities as well as federal funding for scientific exploration. So Sumi joined the UW-Madison faculty in 1948. And it's interesting to note that when he was hired, he had finished his coursework, but he had not defended a dissertation. And it wasn't until the university, our university, told him that he had to complete the degree that he did so in 1953. By 1959, meteorology professor Werner Sumi and engineering professor Robert Parent, UW-Madison engineering professor Robert Parent, realized that they made a productive team. Sumi was adept at making connections across academic lines and had heard about Parent, who was an expert in electronic instrumentation systems and data processing equipment. It was a match. Sumi's scientific ideas, paired with Parent's engineering know-how, proved successful. They were poised to demonstrate the feasibility of putting an Earth observing instrument on a satellite. And how did they arrive at that idea? Well, Sumi's dissertation had to do with measuring the heat budget of a cornfield. And during the defense, his defense at the University of Chicago, one of his committee members said, that's all well and good, but how would you measure the heat budget of the Earth? This got him to thinking about an instrument that could measure absorbed and reflected radiation. So Sumi and Parent set up shop in an engineering building on campus and tinkered with the construction of instruments themselves. They really didn't have research staffs at that time, much less the space that they needed. So they came up in an era that encouraged basic scientific research and collaboration among different disciplines, and importantly, where funding was available to support them, even if their experiments failed. In fact, in 1959 alone, there were 3 launches for their experiment, 2 in the summer, in June, 1 in June and 1 in July, both of which failed. And then again in October, which was successful. So you see Werner Sumi on the left in this picture, and that is the actual size of Explorer 7, the experiment. And their radiometer consisted of sort of ping pong ball-like structures, black and white, to absorb or reflect radiation. So the radiometer provided the first satellite measurements of the Sun-Earth energy balance. It measured reflected and absorbed radiation, producing the first measures of climate from space. Carried on Explorer 7, it is considered the first successful Earth-facing meteorological experiment from a satellite platform. This experiment was a precursor to our climate studies of today. In fact, Sumi said at the time, it was apparent that these results re-emphasize the important role that clouds play in controlling the outgoing radiation. Useful radiation data can be collected from a modestly instrumented Earth satellite. Then, shortly thereafter, in 1961, President John F. Kennedy, in an address before the UN General Assembly, called for the peaceful uses of space. He also called for cooperative efforts between all nations in weather prediction. This led to 2 cooperative research programs, the establishment of the World Weather Watch, a program under the World Meteorological Organization, which is underneath the UN, to facilitate development and operation of observing systems, and then the Global Atmospheric Research Program, also under the World Meteorological Organization, that brought together many nations and observing platforms in order to improve weather prediction over a 15-year period.
The importance of pure science. We realize now that progress in technology depends on progress in theory, that the most abstract investigations can lead to the most concrete results, and that the vitality of a scientific community springs from its passion to answer science's most fundamental questions. Between scientists who accept the responsibility.
So continuing in that vein, President Kennedy, in a 1963 address to the National Academy of Sciences, said, again, we realize now that progress in technology depends on progress in theory, and that scientific investigations are crucial to answer fundamental questions. Also in 1959, A.H. Wainick wrote a letter to Robert Marshall, Dean of the School of Engineering at UW-Madison. Both men knew Sumi well. Wainick was the head of electrical engineering at the Pennsylvania State University and also directed the ionosphere research lab there. In the letter, he says, let's see. I can speak with, from authority about Sumi's activities because of shared membership on committees during the International Geophysical Year. And he says, Dr. Sumi's current meteorology satellite experiment is the only one currently in operation and is about the only imaginative thing that has been brought forth pertaining to meteorology in the US rocket and satellite effort. And being aware of these facts, I was amazed at the circumstances under which these most outstanding work had to be carried forth in a portion of another staff member's office, in another building on campus, et cetera. This is rather strong and bald statement, but I feel that it's much to the point. So who knows if Sumi encouraged that letter or Wainick offered it voluntarily, but nevertheless, it seems to have set some things in motion. He further outlines in his letter what it would take to set up a laboratory at Madison that would be involved in upper atmosphere research, from administrative support to facilities. In essence, he was saying, do what you can to keep this guy at UW and give him the facilities and support that he needs. So amid this backdrop, a backdrop that included some advances in numerical weather prediction, Sumi and faculty colleagues from the Department of Meteorology submitted an application to the National Science Foundation in July of 1963 for graduate level research and academic facilities. And then in August of 64, they submitted a proposal to NASA to construct a space science and engineering center. This concept for a highly collaborative research and academic space is still relevant today. Building on the initiatives introduced by Kennedy, Sumi and colleagues continued to make the case that the atmosphere is an international resource of fundamental importance for human activities, and that many problems in atmospheric research can best be solved through international collaboration. And that the university's teaching and research program in meteorology would continue to be a player in the rapid national development of the atmospheric sciences, but only if they had the facilities in which to do it. The decision was made, and in 1965, saw the founding of the Space Science and Engineering Center by the University of Wisconsin Board of Regents. And in 1968, faculty, researchers, and students moved into what is now the Atmospheric, Oceanic, and Space Sciences building that houses the Space Science and Engineering Center and the Department of Atmospheric and Oceanic Sciences. It was dedicated in 1969, and it was funded equally by the National Science Foundation, NASA, and the state of Wisconsin. So good ideas don't exist in a vacuum. They need care and feeding. And Sumi knew this and was adept at cultivating them. He cultivated interest among university leadership. He was known to visit the dean regularly to deliver good news so that when he needed support, he was likely to get it. And same thing with federal agency leadership on both NASA and later NOAA side of the equation. So he knew how to work with people. So, and here is that next great idea, returning now to taking pictures of the Earth. Sumi's experience and success with Explorer 7 led to more ideas about ways to continuously view the Earth from space. The Spinscan cloud camera, as it was called, revolutionized satellite instrumentation and weather forecasting, and is considered to be Sumi and Perrin's most influential invention. NASA had already been thinking about the problem, but Sumi and Perrin developed a scanning process that captured a full disk Earth image, visual image, about every 23 minutes. Each of about 1,800 scans created a strip of imagery as the satellite spun in orbit. In order to accomplish the scans, the satellite rotated at the same speed as the Earth. Sumi famously said, "The weather moves, not the satellite." And this was, of course, the next of his firsts. Because Sumi nurtured relationships with university and government officials alike, he was able to secure a spot for the Spinscan cloud camera on the Applications Technology Satellite 1 that NASA intended to launch on December 6, 1966, a day that was also his birthday. It was a geostationary satellite and fit the requirements for the camera's needs. Oops.
Take you out of the booth and put you in a booby hatch.
The tape from that 1963 game never survived, but instant replay did. In fact, it thrived. And by the 1967 NFL Championship, instant replay had invaded the locker room.
Coach, we're going to have a play right now. You can see it on this monitor. I hope I can see it. Slow motion now as Jerry Kramer makes a key block for Bart Starr on this quarterback sneak for the winning touchdown. Yes. A super defensive play, but as you will see, Jerry Kramer blows him out of there. Yeah, that's a fine block. And it's
So Sumi's inspiration for the Spinscan camera and making movies from these discrete images came from instant replay that he saw on a Green Bay Packers football game. So he had the idea to stitch those individual images together into a movie that would show cloud motions from space. We see this every day when we click on weather loops on our smartphones. This capability started with him. So looking at the weather on the evening news or wherever you get your news has its roots in the Spinscan camera success. And here is one of those earliest loops from December 1966. So it's wobbly and grainy, and by today's standards, pretty crude, but the concept was successful. Researchers at UW-Madison would soon solve the navigation problem so that the Earth would not bounce around when images were animated. And one short year later, NASA launched ATS-3 on November 5, 1967, and it too carried a version of the Sumi parent camera, though this time the goal was to capture color images of Earth. The multicolor Spinscan cloud camera had blue, red, and green channels and provided color pictures for approximately 3 months, at which time the red and blue channels failed. The satellite was 56 inches in diameter, 57 inches high, and weighed 750 pounds, as opposed to, say, the bus-sized satellites that we launched today. It was carried on a communications satellite that was intended to create a TV link between the US and Australia. The system continued to provide black and white pictures until December 11, 1974. And here's Sumi and colleagues. Bob Parent is on the far left, Sumi is to his immediate right, and they're reviewing print images, ATS images. Sumi, of course, knew that observing cloud motions from space at a global scale meant that scientists could track winds and therefore anticipate or forecast what the weather would be, not just what it had been. This was a tectonic shift in remote sensing. By today's standards, the images are of poor quality, but consider that this sort of continuous imaging did not exist. And further, in the late 50s and 60s, weather reports were still plotted by hand, and we didn't have radar networks until the 1970s. The imaging and data made possible because of Sumi's invention had huge implications for public safety and awareness. It made possible timely alerts and warnings ahead of thunderstorms, snowstorms, hurricanes, and on the radio or on the evening news. Sumi's invention extended the period of weather prediction from effectively 0 days to a few days. He would tell the story about a group of astronomers who wanted to have a picnic at Picnic Point on Lake Mendota and contacted him about a forecast for the afternoon that they wanted to be there. He gave them a window of good weather, after which he said it would rain like crazy, and it did. So his work also made data freely available to many nations that could not afford it. Sumi believed in freely shared data for the benefit of all, and these ideals underpin our research today. For Sumi, collecting the data was not sufficient. As the data volumes were flowing in, he was already considering ways to visualize and evaluate those data to make better use of them. The first visualization tool of its type, SSEC researchers, engineers, and programmers perfected the first GIS system to analyze millions of satellite observations, along with other types of observations in real time, allowing for human interpretation of the imagery. The value of the system was never more apparent than when 42 people died in the Wichita Falls, Texas tornado in April 1979. A congressional delegation visited the Space Science and Engineering Center to see how these visualization tools could help minimize loss of life when severe weather was developing. After that visit, the National Oceanic and Atmospheric Administration and other government units in the US and abroad installed SSEC's system. It's still in use today. Over the years, these systems have matured and spawned other more advanced tools, algorithms, and imaging. When Sumi was asked what he did for a living, he often said, "I take pictures of the Earth." A simple and understandable answer to a highly complex question. With that, I'll hand it off to my colleague, Tim Schmidt, for part 2 of our story. So hold on to your seats.
Thank you, Jean. So I know what you're thinking, we've got a lot of satellites to cover and you're right, we do. So I'm Tim Schmidt, honorary fellow at UW-Madison here. I work for NOAA, National Oceanographic and Atmospheric Administration, just across the street here. So Jean talked about the first 2 of these satellites, the precursors to GOES, ATS-1 and ATS-3. There was a third in the series, which actually had an infrared camera on it as well, just as like the 2 follow-on in the next series, the SMS, synchronized meteorological sensors from NASA. My personal connection to that is my dad was a researcher up in Minnesota, learning how to build and grow these crystals that are used in infrared detection. And some of the crystals that he built were actually used on these early GOES satellites. For example, ATS-6 and NASA's SMS, which were the precursor to the GOES satellites. As a kid growing up, I thought everybody's dad talked about liquid phase growth of crystals and carrier concentrations and the benefits of seeing in the infrared, but apparently that's not the case. So GOES, Geostationary Operational Environmental Satellite. Geostationary is that orbit, that special orbit where it's, the gravitational force is balanced, so it rotates at the same rate as the Earth off the equator there. Operational, not a science experiment. It's got to be there when people need it, which means it's got to be there all the time. Environmental, we call them weather satellites, but even from the beginning, they've done much more than just the weather. We've looked at space weather, sea surface temperature, fires, etc. And of course, the S and GOES is satellite. And that is me explaining how large these spacecraft have become, really big. So that now we'll just look at the GOES series, starting with 1975 is when we had GOES 1, the first now operational in the series. So again, these are similar Spinscan satellites with a visible and an infrared detector on the IR, and also, as I mentioned, some instruments to measure the space environment. So here's an example from GOES 2. On the left, you can see a visible band. So that's the reflected light. So you just get that during the daylight. And on the right, you can see the infrared. It's been color coded. So the coldest cloud tops are colorized, the reds and the greens. So this data is housed over in the Space Science and Engineering Center. Now we put it in motion. So you can see now sunset comes, so the visible goes to black, but the infrared keeps giving you information about where the clouds are and how cold they are, etc., because the weather doesn't stop at night. Another example from GOES 3, Mount St. Helens in May. And on the top there, you can see the visible May 90 and infrared on the bottom. Satellites are really king to watch for these volcanic ash plumes. Why are they important? Planes engines don't like to fly through any volcanic ash because they tend to stop. So anyway, satellites are key for that. So in general, you can see we purchase these as blocks, if you will. So that GOES 1, 2, and 3 were the first generation of the GOES. Then improvements with the GOES 4 through 7 series, more spectral bands, different part of the electromagnetic spectrum to see different things in the atmosphere, and improved monitoring of the space. So there was what's called a sounder. It tells you about the vertical information in the atmosphere. Our first experimental one, it was here on GOES 4. We also had these water vapor images, what you see on the right there. So if you could track that, you can get ideas of the motion in the atmosphere. So now we went beyond just the one visible and one infrared with that series. Another example, Hurricane Gilbert in 1988, again with GOES 7. GOES 7 was a very special satellite insofar as if you look at this, in general, what we want is you draw a vertical line. We always have 2 operational satellites over the Atlantic and the Pacific with 1 operational or backup on orbit spare. Well, you can see there's a gap about 5 years there that GOES 7 was our only satellite after the demise of GOES 6. So luckily it hung on, but again, we're having to move it east and west to better look for the tropics during hurricane season or the Pacific when the flow was coming in. So again, that was an interesting time. I was hired to get ready for this thing called GOES I, which would become GOES 8. And now this went to a 3-axis stabilized platform, which means now the camera's looking at the Earth most of the time. In a spinner, you're often looking at space, so you get better signal to noise. With the benefits of that sounding, we now had an operational sounder and improved space monitoring. And in fact, the first solar X-ray imager to look at images of the sun. So there are improvements in the detectors too, looking at Wisconsin on a clear day. GOES 7, you could see through those detectors, you could see the stripes there, as opposed to a cleaner signal in GOES 8. So again, as we keep marching on, there was the next generation, GOES 13 through 15, which was a different spacecraft bus, so we could operate more during the nighttime with bigger batteries on it, but by and large, the imager was very similar. So for example, then at that point, we were up to not just 2 visible or 1 visible, 1 IR that we had originally on the GOES, but now a 5-channel imager. 1 visible that you get during the daytime and different spectral bands. Looking at, for example, to customize looking at fires or like I say, mid-level water vapor or temperature in the atmosphere. There were some improvements. If you look closely, you can see the edges of the clouds, finer field of view, improvement on one of the channels. But by and large, this series was kind of a clone of the previous. GOES 14 was not ever, or at least for a long time, put into operational service, but we were able to use it to get ready for the next generation. So we were able to put it into special research mode and getting this 1-minute images. So this is GOES 14. So on the right, you can see what, for example, the National Hurricane Center would have been getting operationally, but on the left, a glimpse into the future, what we would get with what would become the GOES 16 or the GOES R series in the future. So this wasn't all the benefits, but again, it could get that into the hands of forecasters at the Storm Prediction Center or other people in the Weather Service, researchers, so we could know how we were going to use this data once we got it operationally with the next generation. So there was Hurricane Sandy as we got it up, moved the coast. Here's another case of thunderstorms in northern Wisconsin there. Again, on the right, 15 to 30 minutes, that's good, but it's not showing what the atmosphere is really doing in this 1 minute cadence. You can see the overshooting tops, the boiling of the convection above Anvil, Sirius Anvil, just a lot of information there. And you're just getting the imagery quicker as well. So again, now we're on to this GOES R series or GOES 16. Geostationary lightning mapper, or GLM, was added. That's an optical sensor to give you total lightning, but also many improvements to the imager as well, which we'll talk about. Also improvements to the space monitoring, and with the fourth in the series, which is not launched yet, GOES U, that'll launch in April of 2024. There'll be a solar corona imager added as well. So you can see that E in GOES is getting bigger and bigger as we go along with each spacecraft. So on the top there, you can see the solar array where we get most of the power. Along that yoke is where the solar instruments are. For example, the solar the SUVI, solar UV imager that looks at the sun, gets images there in a number of spectral bands. But on the Earth facing is where we have the geostationary lightning mapper and this what's called the advanced baseline imager, this much improved imager. So on the previous, generation that we had from GOES 8 to GOES 15 had 5 spectral bands, but the ABI improved that to be 16 spectral bands. It improved the spatial resolution by a factor of 4 or factor of 2 in both directions, and gave much faster coverage of the Earth. So for example, earlier we only scheduled a full disk every 3 hours. Fast forward today, we can get a full disk every 10 minutes. So, and we have these smaller mesoscale areas. So the two views here are what we have the coverage from the east and the west views. So you could see we get that full disk every 10 minutes now, plus that dashed area we get every 5 minutes. And then these smaller boxes, mesoscale sectors are called, we get every 1 minute. Of course, if we put them in the same spot, you can get the equivalent of 30-second imagery. So again, between the two satellites, we have these 4 mesosectors and the 2 full disks and the 2 CONUS. So a lot of data. When I started working on ABI, next generation imager, in the late 90s, it was slated to have 8 spectral bands. Looked at the list of what the Weather Service wanted out there. I said, well, we're not going to get there from here. Working with a number of colleagues here at UW, we're able to convince the powers to be to not have 8 spectral bands, but move to 16 spectral bands. And I can report that's basically become the international standard. Other countries around the world also have geostationary imagers, and by and large, they have 16 and 16 spectral bands. These are the list of all the bands. So we have 2 in the visible bands. We have 4 in what are called the near IR, or think of them as a near visible band, so longer wavelength than 0.7, but still you just need that reflected component during the day, and 10 infrared bands. Those infrared bands have been customized so we can do better job of looking at cloud particle size, hot spots associated with fires, the water vapor structure in the atmosphere, low level structure, ozone in the atmosphere, temperature structure in the atmosphere, etc. There was a memo written to NOAA in 1989 that suggested one of the new bands to be put on the ABI, or to put on rather the next generation GOES. It was a good idea. Memo written in 89. It got on ABI. launched in 2016. So sometimes you have to have a little bit of patience in this business. But once we got the ABI up there, we could show the improvements to the legacy. So the ABI is on the left, and the legacy is on the right. Now we put that in motion. You can see you get the images more frequently on the left, every 5 minutes versus the 15 and 30 minutes on the right. And if you look a little bit closer, you can see better structure in the atmosphere showing up on the ABI with its finer resolution as well. So that's one of the water vapor bands. There's another bands on there to customize to look at temperature. So the hot spots there are color-coded yellow or red. On the GOES 13 on the right, you really just see that one larger spot. This is in Florida, like Okeechobee. Maybe you can see two in GOES on the right, but you can see more of them, and you see them sooner, and you can see the finer resolution with the ABI on GOES 16. As I mentioned, we had these multiple spectral bands, 16 of them. So now there are different ways, a lot of different ways that you can combine them to bring out different meteorological features. So here's what we call RGB, red, green, blue, composite. So for example, bringing out, snow or ice, green, land, clear, blue, and be able to differentiate the type of the water, be it a liquid water or an ice water cloud. Of course, being in GOES, we could also put that into motion. Fast forward, as I mentioned, we have these two satellites, one in the east and one in the west. Here's monitoring the volcanic eruption from Tonga. This happens to be a visible, as you can see, the overshooting tops, the bubbling, and the shadow there as the sun sets. Infrared as well. So again, how quickly that really went from nothing to very cold, and you can see these waves or shock waves emanating from this pulse to the atmosphere. Now, wave didn't stop there. If you look at the lower left there, you see kind of like the emanating circles there going out from this. And those rings actually were able to track multiple times as they went around the globe, interacted on the other side, and came back around maybe up to 7 times. So it was really a phenomenal event, never been before in the satellite era. But to bookend Gene's ATS-1 series, and the most recent one is this GOES 18. GOES 18 was launched in March from Cape Canaveral, and this is actually 2 views of it from the GOES 17, which remember is out over the Pacific, so that's a pretty big view angle, and then the GOES 16 from over the Atlantic. And you can see the plume there as the rocket is shooting off. So that's, GOES 16 and 17, keeping an eye on the next one. So again, we got the first light imagery when it was first checked out in April and May. So the first thing we did was make sure we could make a video of it. So just showing these, stunning imagery. As I mentioned, it was launched on March 1st, joining the NOAA fleet. Basically, this is a partnership with NASA. They'll work with contractors, build it, and then we'll check it out, and then it'll be handed over to NOAA for operations. So again, those 16 spectral bands looking as they should, as we can see. Again, we multiple spectral bands to see different things in the atmosphere. For example, water vapor structure, some of these lows, the jet streak, thunderstorms, overshooting tops, convective cores associated with convection here, outflow boundaries, fog in the valleys, looking at convection again with visible and infrared. Also looking at there's not only smoke here, but also dust as well. Obviously, a surface visibility hazard that's picked up as well. Again, you can just see the bubbling nature, the overshooting tops, suspended sediment that happens to be off South America. And again, some, just monitoring the rapidly changing clouds. Here's, some fires in Florida again, smoke, convection associated with like sea breeze, fires in Amazonia. Again, just beautiful water vapor imagery that we can see from GOES. Again, we'll call it weather satellites, but we can see a lot more than that. So that was when you can see this kind of center position. That was the first part of this post-launch checkout. And we are part of the team that gets some of this first light images before they go out to the rest of the world to make sure that they're okay to provide some images for those or for press releases, et cetera. And the data really look good. There's still some fine tuning. Here we're just looping through the 16 spectral bands, as we can see different depths and some different ways to combine these in to bring out different things, be it fog or dust or other things like SO2, air mass, ash, etc. So again, we're just remarkable imagery. But again, our job is to make sure that the imagery is good for the National Weather Service and private sector and many other users. So here's what it looked like from GOES 16, these 16 spectral bands. 2 visible, 2 near IR, near visible, and 10 infrared. So there's GOES 16, and I'm flipping back and forth between 16 and 18. And yes, there are some differences, because as you would expect, but by and large, you can see how similar these 2 satellites are. But we can zoom in. So here's over Wisconsin. So the GOES 18 is on the left and the operational 16 on the right. So, the blue visible, the red visible, the, near IR bands that tell you about the cloud structure, the fire band, some of the water vapor bands. And again, you really can't to the eye see any difference between those, which is good because they're both well calibrated. So the infrared bands, of course, it's GOES, so we can put it into motion. So you can see this line firing here in south central Wisconsin back in May. That was in the visible. Do same thing in infrared. So here the warm colors are warm temperatures and looking at the heat of the radiating surface. As I mentioned, we can see a lot of things, including fires. So here now is a view from 3 GOES, west, central, and east, central being this checkout. And now the hot pixels are black or red. And we just got a lot more side-by-side comparisons. Again, as I mentioned, sometimes we put those 2 mesos over the same location, so then we can get 30-second imagery of, in this case, these convective activity. So again, starting from 1975, GOES 1 all the way to GOES 18 joining. Remember that and GOES operational, it really means continuity. Let's keep it going. So the second half of this post-launch test, the satellite was moved out to the west position over the equator in 137 west longitude to keep an eye on upstream weather. Will ultimately become operational. So what do? We make another video. Now we get a better view of Alaska. So now we're looking all the way up. Of course, you can see Hawaii. It's near. It's got a good view. Even off the coast of New Zealand, for example, on the edge of the Earth. How do those 16 channels look? Good, just like they looked when the center was over the center of the country. So that's good. But a big low, or bring a lot of moisture into the Pacific coast. Again, smoke in Alaska, fog advection or moving. Again, another view of this low in one of these water vapor images. And again, we're able to bring, these full disk every 10 minutes. And that's, what Vern Sumey envisioned in 1964 when he wrote his proposal for the ATS-1. Again, convection, fires, sea surface temperature, land for surface temperature, thunderstorms, turbulence, just a lot of phenomena that we can see. And a lot of that is leveraging research done right here on campus. So again, we're still in this post-launch checkout phase, but data is really looking good for, and then ultimately in early 2023, GOES 18 would become the operational West satellite for NOAA. Okay, I already said that all. So, I like to say there are two types of GOES users: people that use the data directly and know it. So you're looking at a GOES loop on your phone, or people that use data, but they may not know it. So for example, the data on the cloud information or the wind information or the moisture information went into a numerical model that got a better idea of the current state of the atmosphere, and hence we got a better forecast of what the atmosphere would be. Someone made a forecast off that, maybe you consume that. So basically that means basically everyone's a user. Now I know we only said we were going to talk from 1966 to 2022, but I figured you guys could handle just a little bit more. We're already working on the next generation geostationary constellation. And that's envisioned to have this east and west satellite as we have today, for example, with an imager, a lightning mapper, and a new ocean color sensor. But if you look in the center there of the country, would have this atmospheric hyperspectral infrared sounder. That'll do a better job of profiling the atmosphere to get a better job of where the convection is going to fire. There's also atmospheric composition sensor. Again, this is still all planned, but one of the things is improved band to look, for example, for hot spots or fires. If you look at the top there, you can see that one fire and maybe something to the southwest. Obviously, it's easy to see in the finer resolution, which is what we would get on this next generation imager, or GeoXO imager. There'll be another of core capabilities. As I mentioned, still monitor the space environment, still monitor the sun, data collection system, and a emergency, and some other broadcast systems. So but we're also looking at this infrared sounding, which is a new capability that was really pioneered here at the University of Wisconsin. So as I said, with the ABI, the Advanced Baseline Imager, the imager that we have today, before it was launched, I showed the image on the left there. I said, well, okay, the legacy imager, you get in the red box, but once we get this ABI up there, things are going to be way better. You're going to get the information content of the yellow box, much improved. I think the same story can be made for this advanced sounder, GXX sounder, where again, our legacy GOES sounder was a blue box, but will be much improved, more frequent imagery, finer spatial resolution, and more vertical resolution with this next generation. So, we had, the game changers and the first of its kind, and the orders of magnitude improvement on the imager side, and we're just waiting for that last step on the sounding to give us that vertical information. Too many numbers on here, but the bottom line, you can look at the, top row there and see the ATS series with say 1 visible band. Now we have 16 on the ABI today, and more planned for the next generation. The spatial resolutions, for example, if you look in the infrared, went from 11, 14 kilometers, we're 2 kilometers today, maybe get down to this 1 kilometer on our next generation. They'll start in the 2030s. Why does that matter? These are all water vapor images. And if your job was to tell where the turbulence was, well, you can't do it with, the earliest GOES 7. You have maybe a chance with medium, GOES 8, 12, but it's really till this modern ABI that you could start to resolve some of those wave phenomena in the atmosphere. And as I mentioned, much finer temporal resolution as well. If you recall, August 2017, moon shadow passing over the Earth there. I only mentioned this so nobody's surprised about April 8th, 2024. Further south, less chance of clouds climatologically, but also further from Madison. But we'll always have the GOES to look at the shadows. So, you know, UW Sims, SSEC, the local federal group, you know, played and continues to play a key role. Huge positive impacts in a lot of areas. A lot of that research has been done at Wisconsin. I like to say this, the Wisconsin idea supercharged. We're working on the next generation GOES already. Gene mentioned the replay of the Green Bay Packers, where GOES is kind of like that. You guys are all owners of these GOES satellites. We've come a long way from the one black and white to the color that we get today. I'd like to thank everybody that's involved, and that's, you know, from the pre-GOES, GOES, our next generation, tens of thousands of people. And with that, here's some web pages, and I thank you very much for your time. Any questions?
If you could just repeat it, so these different folks in here also.
So either easy questions or hard questions. I'm happy either way. Yep.
Easy question. All these satellites up there, what happens when they're out of service? Do they stay up there?
Yep. So the question is, you know, we're launching these satellites. What happens to them? So the geostationary satellites, they always have enough fuel on them. Fuel is used for station keeping, moving to different positions. There's enough fuel left on them so they can boost to a little bit higher orbit, maybe. And it's called either the graveyard orbit, or if you want to impress your friends, the supersynchronous orbit. So there are trackers on the web that you can go and see where, you know, GOES 7 is, even though it's not operation anymore. And it's not in that special geostationary ring, because other satellites have to be there, but they're still orbiting up there. And go check that out.
I think there's one in the back.
Okay. Yep.
I spoke to you earlier about regulation of the cell phone industry for water vapor preservation for the satellites. Where is the U.S. and the world regulating cell phones so that we can look at an issue?
Yep. So the question is this whole interplay with the 5G network. So we have, well, there's two ways that we need to use a spectrum. One is, for example, the microwave, although not on GOES, on other satellites, we're just passively picking up, you know, microwave signals, and you can use that to determine things like temperature in the inner core of hurricanes, et cetera. The other way is we have frequency to communicate with these satellites, to either send commands to the satellite or to bring the data back down initially, or calibrate it and we rebroadcast that. So right now, you know, there's this alliance, if you will, of, you know, how to really share that frequency. And maybe there are going to be areas, you know, cutout zones near federal facilities that you can't use some of these 4Gs on your cell phone there. That's not really my area. I know there's still a lot of going back and forth. But I know that, you know, the economic incentives, you know, are in the billions or whatever. So I think stay tuned, I think is all I can say for that one. Yep.
What's the power of these satellites?
What's the
Power? How are they powered?
How are they powered? How are the satellites powered? There's two kinds of power on them. Number one, there's those large solar arrays, you know, and that's where that yoke rotates, so it's always pointing to the sun, so it gets maximum solar power. But there's also some onboard propellant that's been used for station keeping, et cetera. So different thrusters. So for example, as they need, if they have to move. So for example, when we launch this satellite, launched in a lower Earth orbit, hit a thruster, so it goes into more of a geotype or a highly elliptical, another thruster to try to trim it to put it in a nice geostationary orbit. But if we have to move to another location, those propellants that are different chemicals are used for that. So it's a combination.
Is one face of the satellite always facing the Earth
Yep.
in the rotation?
Yep.
And how do you keep it in that, that position with one
Yep.
day? Because it has to do one revolution every day.
Yep.
So how do you
Yeah,
keep that?
yeah. So, okay, so the older generation were Spinscan, so they rotated, and that's where they just looked at the Earth, you know, as they came around. These generations since the GOES 8, as you say, are 3-axis stabilized, so they have gyros on them to help keep pointed towards the Earth. But you're right, they have to keep this Earth. So they keep the Earth facing side of the satellite with gyros or whatever always pointed to the Earth, where the yoke is then following the sun so it can get more solar energy. Are there any questions online or anything?
That's what I was trying to look
Okay.
at. I don't think so.
Okay,
You
okay.
can check the chat if you can reach it. But when I was up there, it was much.
Okay.
Uh,
Yep.
Is the Eugene is the Green Bay Packer clip on YouTube? Is that where you got that?
I did, I got it, I think it was a piece that the Smithsonian Natural History Museum put down. And you may have noticed, it was a clip from 1967, which was actually a little bit later than the one that he saw. But some of those earlier tapes still exist. Yes.
So this one. So, yeah, so. Yep.
What's the nature of the data? There's GOES data.html and then data.html. What's the nature of that data?
Yeah.
I'm curious, it's not images here, it's raw
Yeah.
numbers basically.
Yeah,
And
so.
vectors or something.
Yeah, so what the satellite's actually measuring is going to be radiation from the Earth, be it reflected or infrared. That data basically then gets sent down to the Earth, and that's where the data is calibrated and navigated. So for example, we also look at space so we can get a good idea of what the zero radiant should be, and there's an on-orbit black body that you know the temperature of because there are thermistors in it. So you have this known cold source and this known warm source, and you can do calibration on the ground. Then that data, again, calibrated, navigated, and remapped, and then that gets bounced back to via the satellite. For example, that's what the satellite dishes on top of our building would get. So it's basically a packetized, digitized, scaled radiance that then can again get decoded and stored in nominally, it's in a net CDF file. Those net CDF files for each spectral band, for each sector, are out there on the cloud. There are a lot of different places, but that's then what people would either be used for research or to make images of, go to the Weather Service, et cetera.
We do have a question on Zoom. It is, what do satellites see concerning climate change?
Okay, what do satellites see regarding climate change? The one thing that's really unique about GOES is it monitors this daily evolution of the planet. So we also have polar orbiting satellites, as the name implies, goes over the orbit of like 100 minutes. It goes over the poles as the Earth rotates under it. The good news is you can see the whole globe there. So that's very important for global change, looking at the whole thing. But what that's really missing is some of these things, how they change over the course of a day. And that's what, when you have GOES, especially when you have a ring of GOES, can tell you. So for example, GOES is used to monitor what the real diurnal signature is, say, of clouds. And then that can be compared to a global climate change model to parameterize or characterize that to make sure that is right. There's also a lot of reanalysis where they look back and use all the data that they can. A number of groups have done that starting from the 50s, 60s, 70s. Well, then the question becomes, well, who's right? Well, one of the things they do is they look at some of these water vapor channels, if you will, of around the world and say, hey, well, this, this is a much better matches these observations as the other ones. So it's mostly in fine tuning the models so you have more credence of how good the climate models are. There's another question?
Towards the end, you talked about goes west, goes east, goes central, probably coming. That's still the United States. Are there similar things in other populated areas of the world?
Yep. So we have our goes. There's a number of Europe, a consortium in Europe called EUMETSAT has a number of geostationary satellites there. Well, so there's over Africa, Japan, Korea, China, Russia, all have some geostationary imaging. And as I said, are all kind of moving towards these advanced imagers with something like 2 kilometer infrared, something, like 1/2 or 1 kilometer visible, 16 spectral bands. So again, pretty much wherever you are in the world, you're not that far away from getting a geostationary observation, except maybe if you're at the poles. But of course, that's more often where you get the polar orbiters. So you really need both the constellation. You need the polar orbiters because they see the whole Earth, and you need the ring of goes or geostationary as we have with our international partners, so we can see the rapidly changing phenomena all over the world.
We have another one from Zoom. Do humans see climate change as a threat?
Do humans see climate change as a threat? I cannot speak for all humans. I can at least speak for one human. I think it's a threat. I think things are changing. Some people say things have always changed, which is true, but the rate of change is very, very important. If you don't give chance for the ecosystems to adapt, and as you know, a lot of things have developed in sync, and so you throw part of that out. I think that I don't think there's any question that things are changing. I don't think there's any question that things are changing rapidly, and I don't think there's any question that that's going to have a big impact.
Any other questions? All right. Thank you so much for coming to talk tonight.
Hey, wait, where are the questions for Gene?